is. WebRTC is a standard that enables real-time communication in the browser. This is not a technology that I'm expecting you to use in class. It's just a technology that I personally find to be very cool and compelling. I used it significantly when I was working on my PhD dissertation to develop these like live video and audio applications. It's used by a lot of applications like Google Hangouts and Facebook Messenger, things that use live video and audio in the browser. It was specifically developed as a replacement for Flash, which, as I'm sure many of you know, was removed from most browsers by default because of a bunch of security vulnerabilities. Something that might be of interest to you is that Flash is actually originally a browser extension, which we talked about in the last lecture. However, it was this type of extension called a NP API extension, which actually uses like machine code run on the computer through like a DLL, which enables actually like full access to the computing resources of the system that it's running on. So is this big vulnerability in these browsers because anything that could hijack the Flash extension would basically could gain access to the machine that it was running on. So browsers have done away with that at this point, which is sad for the loss of a huge library of Flash games that were out there, but also it was the primary tool that was used for doing video in the browser for a long time by, not only sites like YouTube, but also like real-time communication apps like Google Hangouts and that kind of thing. So WebRTC is developed as this alternative, specifically for working with video and audio and enabling real-time transmission of that. So one of the, it provides a couple of different functionalities. One of them is providing access to web pages to a user's media devices. So specifically webcam and like microphone access. So typically this wasn't available just in the browser from a JavaScript API before the advent of WebRTC. So WebRTC provides this API, specifically this here at the bottom, this navigator.mediadevices.getUserMedia API call, which will give you access to these devices. So there's a quick demo I'm just going to run through to show you kind of how this works. Let's see if I can bring this up. All right. So this is just a simple example. Let me see if I can bring up the code for this. That shows how you can actually get access to the webcam video feed. I need to probably actually disable my video. Let's see. Am I not sharing my screen anymore? Can someone's?
You are. I can see your screen.
Okay, I'm still sharing my screen. Okay. All right. So just to give you an idea of how this works, this is just a simple page that has, just look at the elements real quick. So this is actually a video element that is just empty video element that's on the page, and we have a button here that triggers this event listener, which calls this init.e, which calls this API of interest that we were talking about, this navigator.mediadevices.getUserMedia. So the response from this gives us a stream object in return. So and then once we get that, we go into this handle success function, which we call get video tracks on it. So I'm just going to go ahead and initiate this in the debugger. So we get the video tracks, which show us things like, which give us an ID for the stream from that video track, which we can load up, but also tells us like the name of the device. So this is my webcam, the type of stream that it is. This is video. And then we can, simply one thing that we can do is just say, this window object is, what is this? Oh, that's not necessarily what we're using, but we can attach it to the source object for this video element, and then my vase is just appearing here. So the video stream gets attached to this video object. We can use this to either show video from these webcams, but we can also use it to like get the data from these. So we can get like the bit streams representing the images, or in the case of the microphone, we can get a bit stream representing like the audio stream, and we can work with that audio. All right, so that's enough of that example. So yeah, if you're wanting to work with a microphone or webcam, this get user media API is what you're going to want to be using. All right, let me stop this and re-enable my webcam. Okay. So yeah, that's a very useful functionality that's built into WebRTC. But maybe the more interesting functionality, oh, and if you want to learn more, there's a link here in the slides to some documentation for how to get started with that. But maybe the more interesting functionality that's available with WebRTC is how do we actually transmit this media across the internet between different browser-based clients. And WebRTC has APIs that handle that transmission across the web. And it handles a lot of the nasty details that are associated with that. If you've ever worked with video or audio before, you know that it's not just sent, or it's not just handled in a raw format. Typically, we will do what's called compression and decompression, or encoding and decoding, which basically makes our video streams, which if we just store it as like a raw collection of like a bunch of images as video frames, then it's just ridiculously large data sizes. So we have to do what's called compression, which is kind of like a zip technique, if you will, for video. And we're not going to get into the details of that, but just know that WebRTC does a lot of that for you. If you ever heard of like H.264, that's a video compression algorithm that is fairly well known and popular, although there's some like legal issues surrounding it. But it is one that is supported by WebRTC. And so WebRTC handles all that for us. It also handles how to establish peer-to-peer connections. So one of the more powerful things that WebRTC enables is that we can send these video and audio streams directly between two different clients across the internet. We don't necessarily have to have a server in the middle that is taking in that video as well as broadcasting it or transmitting it to other clients. If we were going to create a video environment or a WebRTC application where it's just two people calling, we could easily set up a connection where they're just transmitting the data directly to each other, which saves in costs and hosting these kinds of services, and can it makes it simpler on some levels and more complicated in others. I'm not going to get into how you actually implement these what are called peer connections. There's an API called RTC Peer Connection, which sort of enables all this. I'm not going to get into the API, but I'm going to talk a little bit about some of the details that go into making this work and why it's kind of interesting as well as potentially a little bit confusing. So the general process for establishing one of these connections happens through what is called signaling. So WebRTC, the API, provides basically all these things to get access to media, to establish connections to other WebRTC clients. However, it relies on the developer to develop this mechanism called signaling. So what that typically means is whenever you're making a call to somebody else, you generate some data that says that's called an offer that you then send to the person you're trying to call. They can look at that and then say, okay, I want to accept this call, and they'll send back an answer. And typically that is just like string data that has properties for the connection information. To give you an idea what that looks like, typically it is encoded in what's called a session description protocol, or SDP. This is a little bit, what's the word I'm looking for? Not archaic, but esoteric maybe. It's just a lot of parameters that are getting set about the call. So each of these is sort of like a key value pair or a set of different properties to know for the call. And this is probably only about an eighth of the amount of like configurations that would be involved here. But this is all like, generated for you automatically by the WebRTC stuff. Okay, so and then and when I say that you are doing signaling, you are transmitting these strings between your different clients. But WebRTC doesn't have like the built-in tools for you to do that. You have to have a web application that will do that for you, basically. So we can think about mechanisms that we've already been looking at in this class. So you could easily do this with something like Socket.io, where two people join a room, and then you could use Socket.io messages to transmit this signaling data back and forth between the WebRTC clients. WebRTC doesn't do that for you. You have to specifically enable a way to get that those configuration strings back and forth between your different clients. All right. So, so WebRTC enables you to establish peer-to-peer connections. There are some difficulties involved around this. One of them is what are called NATs. And I'm assuming that some of you have encountered these before or know what they are. I'm wondering if someone wants to take a stab at explaining what a NAT is, what it stands for, and what it is.
Does it stand for, or what is it? Network adapter type?
Not quite.
Okay, because I only see it in consoles, and usually when I'm like testing a connection in my console, it'll say like using that type of 1, 2, or 3, and I hear like 3 is like the worst one you can have.
Yeah, so there are different types of NATs. So anyone, and yeah, it is an issue on consoles as well, because you get the same sort of issue where you're trying to establish connections, potentially peer-to-peer. Valentine, were you going to take a stab at it?
For NAT?
Mm-hmm.
So it's like a network address translation. That's what it means, right? So it basically translates private IP addresses to public IP addresses. So let's say we are in a local area network and you're trying to like access the internet. The NAT actually translates your local IP address to an internet, a public IP address, basically.
Yeah, that's actually exactly right. Um, I guess one question I have is why would we want to do that?
Um,
There's
because
there's
because
two prominent reasons.
yeah, because local IP addresses can reach the internet. You can access the internet with local IP addresses, and I think security as well, but I'm not too sure.
Yeah, so that's basically right. The one, so yes, so if you're on your home networks at home, or even at like large organizations like workplaces and things like that, we don't actually use what are called public IP addresses. We use private IP addresses, which aren't actually routed on the public internet. Um, they just sort of sit within the local area networks of those organizations. So what a NAT actually does is it maps from that address space to a public IP address. Um, and one of the primary reasons that you want to do this is that it's getting increasingly more expensive or more difficult to actually get like the original IPv4 IP addresses. IPv6 is not such a problem, but with the original smaller IP addresses, there was not that many to be had. So this was a way that we could basically serve more computers on the internet by using private IP addresses on our local area networks that were basically behind a router, which only had one IP address for like the entire network. What happens is, say I want to make a connection to some web page on the internet. I try to establish a TCP connection to that public IP address, which could be anything. Um, However, when I'm trying to do that, the connection has what's called a source port for my socket connection, uh, which generally is just random on my computer. And then I send that across my local area network, and it hits the router, which is usually what's running the network address translation um, program, and then translates that into public IP address communication, which gets transmitted on the internet. So at that point, it will change the source IP address in the IP packets that are getting sent from the router, and it'll also change the source port. And then it keeps a big table of that basically maps the external source ports to the internal ports. So whenever you're getting a connection, whenever you're getting packets back from the broader internet that are supposed to be communicating with your hosts, it looks up based on what port that's coming in on their TCP or UDP connections, and then uses that to figure out which private IP address it should send it to. So this has a side effect of creating a security measure, and that if I haven't tried to make a connection to something on the broader internet, then there's no way for something that's just in the internet to actually communicate with my computer directly. It doesn't know what my ports are. There's there's nothing in the network address in the router that would, if it gets just a random port that nothing is listening to, it can't get through. And so this effectively is sort of like a firewall at the same time, and gives us an extra layer of security. However, whenever we're trying to, well, I guess let me ask the follow-up question is why is this a problem for trying to establish peer-to-peer connections? I might just ask Valentine if it seems like you've thought about this a little bit.
So first could be latency, like delay. And the second could be the fact that, I'm trying to reach, someone directly. And so like on the public internet. So the translation might not be a good bet for it because of the
Yeah.
translation it does. So
Yeah, so there's no like, if there aren't any existing translation rules in the network address translation table, then there's no way for like an external person to like contact my computer directly.
yeah.
So that makes it very difficult to establish a peer-to-peer connection, because typically that's, if I want to establish a connection with, say, Valentine's computer, my computer is at home, it's on a NAT. Valentine, I'm assuming, is at home. This computer is probably on a NAT. So we have to deal with getting through these things to actually make a peer-to-peer direct connection, instead of both of us like going directly to a server. So the question becomes, how do we work around it? And this is done using a technique called session traversal utilities for NAT, or STUN. And typically this is done with like a server that is used to identify like the public facing IP address and ports of a client. And so what does that look like? Well, so here I have my client and my NAT firewall and a STUN server here on the right. And so what I do is I initiate a connection to the STUN server. So I make a request to it, which basically all it's doing is saying, who am I? And so this would probably just be a TCP connection, or I guess TCP or UDP connection. It says, who am I? It gives my source IP address and port, which again, I'm on a 192.168, which is a private IP address, with a port, which is a random port number. And I'm sending it to a STUN server, which is sitting somewhere on the public internet. So it's going to hit my NAT. And when that happens, the NAT is going to add my private IP address, which is 192.168.1.12, to the translation table that it has. And it's also going to pick another port to basically forward to my IP address, my private IP address, whenever it receives data coming in from externally. So it changes, so it actually goes into the packets for the TCP connection. It changes the source IP and source port, and then forwards that on to the STUN server. So when it gets to the STUN server can actually see what the what the public IP and the public port are coming from the NAT. And what it does at that point is it just goes ahead and connects, and it sends back a message to the original client. And so this goes back through the NAT, and it tells the client that, okay, this is your public facing IP. So your router has this IP address, and it set up a translation table entry for you on port 8392 in this case. So what the client can then do with that is it can communicate it to another remote peer, which can basically hijack that translation table rule. And so what you end up having is, say, if I did this with the STUN server, I get told that this is my public IP address and my port. I can then transmit that data to Valentine, who can then use that address translation table entry. They can basically use that to bypass my NAT and connect directly with my computer at that point, establishing a direct connection. So this works for some NATs. There's specifically some types of NATs that associate an external port translation table entry with a particular remote IP address, in which case you cannot do this because it checks like where the traffic is coming before it allows it back through. So I believe that's called what's called a symmetric net. And so in that case, you can't do it. And so in that case, we have to figure out a different workaround. And that in particular is called turn, or traversal using relay NAT, or maybe it's relay for NAT. But basically all this is an external server that instead of doing a direct peer-to-peer connection, it's basically just serves as a link between two clients. They both connect to it through their NATs, which is easy to do. And then they specify like a key or some kind of credentials, and then they'll send data to that server, and it just basically relays it to it just acts as a relay. It just copies the data and sends it over to the other one. So you're not actually doing a peer-to-peer connection. You're doing a connection through just an intermediary. So that's, it's not the best case scenario. You're sort of falling back onto doing centralized server relay data at that point. But the way that NATs are these days, we can't necessarily 100% rely that we're going to be able to use stun to poke a hole in them. So, and why we're trying to do this is, we're trying to establish connections between our clients so that we can send streaming video packets or streaming audio packets, or both. Or WebRTC actually enables you to just sort of send generic data as well. So we can use these to develop or to set up these direct connections. Together, Turn and Stun are what are known as ICE, or Interactive Connectivity Establishment. Basically, we have several what are called several different candidates for establishing a connection. One of them would be doing Turn to set up sort of this hole in the NAT and doing a direct connection, or Stun, and then or Turn where you're doing a relay. In the rare case that both people are on just public IP addresses that are on the internet, you could just do straight direct communications, but that's a fairly rare occurrence. And then once we establish these candidates, WebRTC basically chooses from the best one to establish a connection to send audio, video data between the browser clients. All right, and just as a part of that, you can see in here there's some ICE information. Whenever you set up WebRTC connections, you also have to set up things like stun server IP addresses and things like that it'll use. But in this case, we also include some of the credentials for the ICE protocol, which is basically some tokens that we use to verify that who we're actually talking to through these connections set up through ICE is who we're expecting to talk to. So that's also sent in this session description protocol data that is getting communicated back and forth in our signaling procedure. So, okay. Right, and yeah, so we're going back to doing the signaling where we're communicating the session data through the STPs back and forth. And just to kind of give you an idea of, this is like sort of a kludgy demo that kind of shows this procedure. I think I have to like stop video again here. So first thing we do is, if you'll recall, we do the get user media API to get a webcam view for or the webcam media streams. We can also get the microphone streams this way. We said we'll call create peer connection, which just basically creates the API object for the connection. And so we create this offer SDP again, which is just all of this configuration data for the connection. We can send that through to the other by our signaling mechanism, which again is just something like socket.io probably. And then, okay, so we set the offer and then we create the answer, which again is, so this is the remote connection, or the remote peer creating an answer SDP, which is again just specifying a bunch of configuration data for that. So we set the answer, and so that sets up this connection where we're actually transmitting video through WebRTC by exchanging these different configuration data strings. It's I'm not going to get into how the APIs work, but I just wanted to give you an overview of some of like the high level ideas. And there are other examples here on these URLs if you're interested in coming back. If you go up the directory structures here to like samples, there's a couple of other interesting things. And you know, these you can use the debugger to go through these and look at you know, what exactly is going on. It's, you know, they have code that's setting up all of these different calls, and you can look and see how they're setting up these data connections if you want to go back and look at that. All right. Okay, so and just to step back for a second and to think about sort of what this enables. Whenever RTCP was WebRTC was initially released, the big thing was to be able to support these peer-to-peer connections, which, you know, is really exciting because we don't have to necessarily have a lot of server infrastructure to support that. However, in my experience from actually enabling these types of video environments, that oftentimes they do actually end up relying on, I'm going to stop this so I can start video. They do actually end up relying on centralized servers to be able to communicate these data. And that has to do with several reasons. One of them is if you have a peer-to-peer sort of environment, and, you know, if, say for example, this Zoom call that we were having is set up in peer-to-peer, which I'm assuming it's not. I don't know exactly how Zoom is implemented, but you know, if we were doing purely peer-to-peer transmission, you know, we would have to establish an exponential amount of connections between all of our clients, right? So like if you're just doing 2 connections, then that's just one, or 2 clients, that's just 1 connection. If you're doing 3, that becomes, you know, 2 different connections. Or 3, if you're doing 4, that becomes 1, 2, 3, 4, 5, 6. It becomes, and so this number of connections that you have to end up establishing in a sort of a peer-to-peer configuration ends up increasing, like, I think in like factorial, which is, I think, faster even than like exponential. So it's just like this huge increase in like the number of connections that you're having to make. And, you know, data transmission is having to get like duplicated all over the place. So if we're just doing it with a centralized server, that's just 1 connection per client, right? And we're only uploading and downloading like the video once per client, which is actually a really good thing for us because, you know, our local internet connections might not support me sending out 20 copies of my video stream to everybody, right? So that's one reason why you want to use a server. I guess the core takeaway, though, is that WebRTC can be used in a server situation. Like the peer that I connect to doesn't have to be a browser. There are servers that are set up to take WebRTC connections and to forward them to other WebRTC clients and other browsers. So you end up still getting this like centralized server architecture. One of these, if you're interested in looking at it, is called this Jitsi Video Bridge application, which is basically just a WebRTC video forwarding service that enables, they have like an application that goes along with it called Jitsi Meet, which is basically just enables Google Hangouts or Zoom, but it uses WebRTC in the browser. So, and it's all open source if you want to go look at that, how that's implemented. I'm fairly fond of this project because I used it in my dissertation project, which used streaming video connections. So yeah. And again, I'm not expecting you to use this in your final projects or anything like this. I think it's just a very interesting and exciting like web technology that's out there, and it's fairly new. A word of warning is that while I called it a standard at the beginning, it's still sort of in significant development. And so while the browsers do like interoperate, they support different like standards, and some of them support different feature sets than others. And if you're like communicating between different browsers, then maybe those features aren't available. So there's a lot of potential difficulties there. If you want to learn more about what WebRTC is and how to implement at least simple applications with it, this HTML5 Rocks WebRTC tutorial is pretty good. I think that is all I have for today, but hopefully y'all found this interesting. Is there any questions that I can answer for people about like this technology and or why you might want to use it? Oh, it seems like there isn't. But thanks for listening to me. This may or may not have been useful for you, but I think it's an important web technology that's out there right now that people should be aware of. And I guess if you do end up working with it, I will warn you that there are lots of little details when you get down to the APIs that can be hard to follow. But it is a fairly usable technology once you kind of get it set up. So, but I guess that's all I have for today in terms of actual lecture material. If people, if people want to talk about their projects or anything like that, I'll hang around. But otherwise, that's pretty much it for today. So.